All right, great. So thanks everyone for your attendance today on today's webcast that's going to discuss replicating data from MongoDB to Snowflake using Upsolver. My name is Jason Hall. I'm a senior solutions architect for Upsolver, and I'll be your presenter on today's session. Just a couple housekeeping items. We are recording today's call, and we'll be sharing the recording after we wrap up. You'll be feel free to send that recording to maybe anyone on your teams that couldn't attend today, or anyone you might want to share the information with. For the benefit of the recording quality, we have muted everyone's phone line, but we do want to encourage interaction. So if you do have questions or comments that you'd like to send over to me, please use the Q&A function within Zoom. You should see a button in your Zoom console labeled Q&A. That'll allow you to ask questions. I'll be keeping an eye on those questions in real time, and we'll do my best to answer any that do come up. And for questions that I'm not able to get to in real time, we should have time at the end of the session, and I'll be able to rattle through as many of them as come in. So please get all your questions in. Definitely want to hear your feedback and comments, and that's the best way to get it to us. So on with the session. For those that have not come across Upsolver before, just a quick introduction. Upsolver is a self-service data ingestion platform for high-scale workloads. And we'll quantify what that is here later in the session. But customers that need to work with big data sources, complex data sources, and ingest those sources into data lakes and data warehouses, that's where Upsolver fits. And you can see that's proven by the section of the slide down in the lower right-hand corner. The majority of Upsolver's customers are working with very large sets of data, right? So almost 10% of our customers processing at least a petabyte of data a month, and more than half of our customers processing 10 terabytes of data a month. So that really is our sweet spot, and where we add most value to our customers is in helping those customers work with and ingest and process very high-scale workloads. Right? And that's what we're going to be talking about today, specific to MongoDB. So with that said, kind of an agenda for the session today, we'll start by talking through the MongoDB to Snowflake use case in general. Right? Why are customers choosing MongoDB? Why might we need to get data to Snowflake? And that should hopefully provide a lot of context around how Upsolver can ingest Mongo to Snowflake. We'll then talk about some common approaches to MongoDB data ingestion, both from the MongoDB platform itself, as well as some APIs and interfaces that data ingestion can occur from. We'll talk about a pretty important concept when it comes to MongoDB, and that specifically is schema handling. Now, schema handling is important regardless of your data platform. You know, how you manage and map and process schema changes is a critical component of any data ingestion pipeline. But I think it's very important and a little bit more complicated in MongoDB, specifically because of the semi-structured document approach to how data is stored in Mongo. So we'll spend a little bit of time discussing some considerations around handling schemas when ingesting from Mongo to Snowflake. Then we'll get into the Upsolver approach. So how does Upsolver handle MongoDB to Snowflake ingestion? And then we'll spend a good amount of time in demo today. So I really want everyone to get a feel for the product itself and how this process works. And so most of the session today is going to be spent in a live demo, and you'll have the chance to see the product and also ask any and all questions that you have about how Upsolver works. So why MongoDB to Snowflake in the first place, right? And so MongoDB was founded or first brought to market in the 2000s. I want to say it was 2007, 2009 time range. And it became very popular very quickly because of some very unique capabilities that it brought to market. I actually included a screenshot down at the bottom from a site called DB Engines that does a monthly database popularity rating. And there's a lot that goes into this. They don't fully disclose their algorithm, but it's a combination of social media posts and Stack Overflow chatter and market share metrics. There's a lot of different numbers that go into popularity, but I think as a reference point, it is helpful to just kind of understand trends, right? So what databases are quote unquote popular, and is that increasing or decreasing? And I thought it interesting that of their top 10 databases, and you could argue, are some of these real databases or not? I love talking to Microsoft folks and asking whether or not we consider Microsoft Access a real database. But regardless, you can see MongoDB has become the 5th most popular database across the industry. And maybe more interesting than that, MongoDB is the most popular database that doesn't fit the traditional relational model that we're used to. In other words, rows and columns, right? 1 through 4 all would be considered relational databases. The other thing that I think fairly interesting is if you look over to the growth metrics over on the right, MongoDB seems to be showing the highest growth when it comes to popularity. Right. So I think this is just an interesting perspective. We're going to talk about why I think MongoDB is growing at this rate, but the industry is kind of verifying through a variety of factors that not only is MongoDB a very popular database, but it is a database that seems to continue to be growing in popularity. Now, why is that? We mentioned MongoDB is the top database on this list that doesn't fit into what we would consider a traditional relational database, right? MongoDB wasn't necessarily the first database, but maybe the most popular database to natively support storage in a semi-structured document model, right? Data in MongoDB is stored effectively as JSON, right? Now, technically it's BSON. It's a slightly different format, but for conversation purposes, we can think of it as JSON. And that means that data is not stored as a row, it's stored as a JSON document, right? And metrics are not stored as columns, they are stored as fields within the JSON structure. And this allows for a very different model of storing data, right? We don't have to define schemas up front, right? We can store documents for years with different columns and different data types. There's no requirement that documents, each document or each row, as we often think of it, in MongoDB has the same schema as the document or row in front of it. Now, there are ways to enforce schemas in MongoDB. So if you want a more rigid schema structure, you can force it, but it's not required, right? And that makes it a very popular database for application developers because they don't have to very rigidly define their schema up front, and making schema changes becomes much easier as the application evolves. Right? I think one of the second reasons why MongoDB has really grown in popularity is that they offer native HADR support through its replica set architecture, right? HA and DR within MongoDB was not, I don't want to call it an afterthought, but was not kind of cobbled together using other third-party technologies as it was for some other data platforms, right? MongoDB has been built from day one to support a replica set-based architecture, which makes for HA configurations and DR very simple. Failover is quick and simple, and really the database was built from the ground up to support high availability. Similarly, it was also built from the ground up to support sharding of data across different nodes of a cluster, right? Sharding in many database platforms is a very difficult process to configure and often involves custom development in order to support. With MongoDB, sharding is really just a few configuration changes, and it's natively supported in the database itself. And then lastly, I think MongoDB was one of the database platforms to, I don't want to say it was the first or maybe even the earliest, but it was certainly one of the more successful databases to get very wide adoption of its cloud-hosted architecture, specifically Atlas. Some of this may be because of the developer preference for MongoDB and developers really being more eager to move into the cloud sometimes than legacy IT providers, but a lot of MongoDB's growth and popularity has been fueled by its cloud offering Atlas. Right? So for all these reasons, and honestly, for those of you on the call today, MongoDB has become a very popular database for storing, semi-structured data. Right? Now, with that comes a few considerations. I titled this slide downside, but I think a more accurate description is just things that you have to consider when storing data in MongoDB. And specific to today's use case, it's that analytical queries can be more difficult than they had been against relational tables, right? And there's a few reasons for that, a couple that I'll call out. In a MongoDB architecture, documents are stored within collections, right? In a relational database architecture, you have rows stored within tables. In MongoDB, you have documents within collections. Joining of tables is fairly straightforward, right? Joins have existed for dozens of years. There are lots of different join types that are common across a variety of analytical use cases. MongoDB does not natively support all join types. They do kind of support a left join through a lookup approach, but it is not trivial in some cases and not possible in other cases to join different collections. And that's a very common use case in analytical workloads, especially when you have dimensions and facts and queries that you need to enrich with data that comes from other sources. MongoDB's answer to this lack of joins in many cases is they want you to store as much data as possible within the document itself, right? So rather than having to join two tables or two collections together, if you have reference data in one collection that you need to include in another, they would rather you just nest that same data within the original document. And that's all well and good. There's not a lot of performance overhead in doing that. The challenge becomes it can lead to data denormalization. You have to be very careful if you start denormalizing your data and stuffing more data into single documents, because if data changes, if you have changing dimension types, you have to be very careful and make sure that those dimensions are changed throughout the architecture. Another challenge with MongoDB is that while the replica set and sharded architecture is relatively simple and straightforward, the scaling out of a Mongo deployment for ad hoc analytics complex and expensive, right? So ad hoc queries are run by a BI platform to drive analytics. You may have to scale out a replica set, and the scaling out of that replica set could be very complicated and very expensive, especially if it's for an ad hoc query that's going to run once and may not run again for a period of time. So for these reasons, and honestly, these are on top of the reasons why many data integration architectures exist. Many users will try and get their data from MongoDB into a data warehouse or data lake so that they can run analytical queries against a platform that's more purpose-built for them, right? So this scenario of possibly wanting to get data from MongoDB into Snowflake, and I'm using Snowflake as an example data warehouse here. There are plenty of data warehouse architectures that would drive very similar benefits. But the idea that we might need to get data from Mongo into Snowflake, this has existed for dozens of years. Many customers are also replicating SQL Server and Postgres and MySQL data to Snowflake. But for those same reasons and the reasons that I have mentioned on this slide, getting MongoDB data into a data warehouse for analysis is something that customers often find needs to be a critical component of their data architecture. Right? So hopefully that provides a little bit of context. Now, how do we do that? All right. So there's a variety of methods, and I'm not going to outline every single method on today's call. But a very common method uses an API or a function of MongoDB called change streams. Change streams have been included in MongoDB for quite some time now. There's been lots of enhancements to them, but for all recent and current versions of MongoDB, change streams are natively supported. And change streams provide a mechanism for effectively logging data modifications to a stream that can be ingested into other applications, right? So in MongoDB, for example, a new document that gets added to a collection, a document is deleted or a document is modified, those typical kind of DML operations that we think through. Change streams is MongoDB's approach to logging those changes somewhere that can be read by an external source. Change streams are available in all MongoDB deployments with the exception of standalone databases. Now, I don't find very many customers using standalone databases. Most Mongo deployments are going to be either replica sets and or sharded clusters. But if you are using a standalone Mongo database, this will not work, or change streams will not be available. But it is available in all distributions of Mongo, whether you're running on Atlas or running your own deployment of MongoDB. The change streams are pretty ubiquitous and commonly available. I do get some questions from Mongo customers about whether change streams are the same as the Mongo op log. Similar in theory, and change streams are actually built kind of on top of the op log, but the op log cannot be reliably used for data ingestion. The op log is used natively in MongoDB for replicating of transactions between replica set members. That's really its core purpose. The op log, though, does not guarantee that transactions will remain available for data ingestion purposes. The op log will roll over. It might delete things from it when you still think you might need them. So you really can't rely on the op log for data ingestion. If you need a reliable data ingestion API, you'll want to configure change streams. It's built on top of the op log and provides a guaranteed delivery of DML modifications to document data that can, again, be ingested externally to MongoDB. Right? So you might hear me reference change streams again. All change streams is a built-in native function of MongoDB that's very commonly used to ingest data modification, or CDC data, as it's often summarized, change data capture, externally to Mongo. So one of the options for ingesting data from MongoDB is to build your own CDC architecture. There are lots of APIs and solutions out on the market that can be combined to build a data architecture that ingests data from MongoDB and writes it anywhere. Again, I'll use Snowflake as the more common data warehouse platform today, but this applies to really anything. And so the way that would work is you would have a custom application that consumes change stream events. Right? Pretty simple syntax, very easy to find online for building an application in a variety of programming languages that can read change stream data. They call them watch commands. You're watching a collection for change stream events that come off of MongoDB. That application then would commonly write those change stream events to some message broker. Most commonly I see Kafka used for this use case, and I'll explain a couple of reasons why in a second. But really any message broker, whether it's Kinesis, Azure Event Hub, should be used to accept these change stream messages from the application that's reading data from MongoDB change streams. These messages themselves are pretty simple JSON data structures, so nothing overly complex about the change stream messages. Once that change stream event gets onto a message broker like Kafka, then you could take that message and write it into your data warehouse. All right? And there are lots of APIs that allow, for example, taking an event from a Kafka topic and writing it into Snowflake. I'll provide some examples here in a minute. So with a few services, right, change streams themselves, some sort of custom application, some sort of message broker, and then some sort of ingestion process, you can get data from MongoDB into whatever the data warehouse that you might need to write data into. Now, there's an open source platform called Debezium, which can actually simplify this architecture a little bit. Debezium is a very popular open source CDC platform. It provides connectors to a pretty wide variety of databases, MongoDB being one of them. And so if you don't want to write your own application to read change stream events from MongoDB, Debezium can do that for you as more of an off-the-shelf open source offering. Debezium still does have a Kafka component to it. So Debezium can read from Mongo right to Kafka, so it can handle part of the application architecture. But it is nice for customers that don't want to have to write their own applications to read change stream events and write them to a message broker. So just to kind of put some of these pieces together visually, again, very common do-it-yourself architecture for integrating data from Mongo to Snowflake would be to have MongoDB over here on the left. Maybe use Debezium to read change stream events and write them into Kafka. And then you can use something like a Snowpipe streaming to take events off of the Kafka topic and write them into Snowflake. Right? Snowpipe streaming is still relatively new. Don't know a lot of customers using it in production, but it should offer a scalable, I'll say scalable and reliable option for reading data off of Kafka and writing it into Snowflake. So this could be a theoretical do-it-yourself architecture for customers that do want to integrate MongoDB data into Snowflake. Right. So that's kind of the pipeline architecture, as I call it, right? One approach to getting data from Mongo to Snowflake. But something that has to be considered is the fact that the MongoDB data structure does not easily map to the Snowflake data structure one-to-one, right? We talked about the fact that, most Snowflake data is organized into tables, right? You've got rows and columns. MongoDB data, for all intents and purposes, is effectively JSON, right? Which is not easily transformable into rows and columns, right? I have an example from MongoDB Compass over on the left-hand side of the screen. This is actually the data that we're going to be working with in today's demo. But you'll see a MongoDB document may, for example, have nested structures, right? So as an example, let me get my little spotlight here. This customer field that you see in MongoDB is an object that contains nested fields within it. We've got an email address, first name, last name. We then have a second level of nesting here with an address field that has additional subcomponents, right? So JSON data structures often include many nested fields, sometimes with dozens of levels of nesting, depending on, the data structure elements itself. And within this nested structure, this maybe isn't the best example of this because notice that each of the child fields are strings, but that is not often the case, right? Often you may have numbers, you may have strings, you may have a variety of data types within those nested field definitions. Right? Also, because MongoDB is quote unquote a semi-structured or schemaless type system, there's no guarantee that even when the data fields are the same, that the data within those fields are of the same type, right? For example, I can see postcode here is written as a string, but it's a 5-digit number. That could be very easily represented by an integer. And so we could have different documents within the same collection with data type mismatches in similar identical field names. Right? That's something that can't easily happen in a relational database, but it can easily happen in MongoDB and is actually relatively common. Right? Now, another thing that needs to be considered in terms of the data model is that MongoDB natively supports array structures. So beyond simple nesting of fields, you can have an array field that includes multiple items with data nested inside of them, right? So this items array in my JSON structure, in my case, has 2 items to it, item 0 and item 1, and each item has some nested data inside of it. So how do we handle arrays in a relational database? That's something that we need to consider, right? When we take a nested JSON structure and map that to rows and columns, how do we want to handle the array elements, right? So all of these are things that need to be considered, not just within the pipeline architecture, which we talked about a minute ago, but in the data translation, right? As we move from kind of a semi-structured JSON document model into a Snowflake data model that's primarily organized into rows and columns. So one example of how we can do this, and we'll show you a few examples as we get into a demo here, And this is kind of what I see most commonly. This isn't necessarily the right way, but it is a common approach, is that you can take nested fields within that JSON document structure and simply map those to separate Snowflake columns. All right, so instead of seeing a customer record with a first name and a last name field inside of it, we just extract those into a first name and last name column, right? So just effectively taking out the nested structures. With arrays, there's a few different options that you have depending on what you're looking to accomplish. Some use cases will take arrays within JSON, convert them to strings, and then write them into Snowflake as strings. Now, the array processing then is going to happen downstream via some type of transformation logic. But if you're not sure how you want to handle an array, oftentimes the easiest way is to just write it as a string, and then we'll worry about it later. Another approach to working with arrays is that we can flatten an array. And this concept of flattening an array effectively says, let's take the items within an array and convert each item into its own row. So if an array has 3 items to it, instead of writing 1 row for that array, let's write 3 rows, 1 for each item within the array. So flattening is a fairly common approach if the use case requires it, and that's another way that we can handle arrays. Now, within Snowflake, the easy button for this, when it comes to ingestion, is to leverage Snowflake variant columns. Right? A variant column in Snowflake, kind of implied by the name, the data type of that column is going to vary and could contain any type of data. There's a lot of formats, but for the purpose of today's conversation, this variant column would include JSON, right? The JSON that came from the source, and then we can decide what to do with it in our Snowflake transformation logic, right? So rather than worrying about extracting nested fields or flattening arrays, let's just stuff everything into a variant column. We'll kind of get the data from the source to target as is. And then in our Snowflake transformations, maybe we use something like dbt to further model data after it's been written to Snowflake. We'll take those variant columns and maybe break them out into multiple table models. Right. So again, just a few considerations that I think are important to think through a little bit. I don't want to say you shouldn't think through data model schema mapping when working with relational data and writing that into Snowflake. But when working with semi-structured data like JSON, you just have to, I think of it a little more. That's a good way to put it. So with all that said, what is the Upsolver approach? All right. So we talked about kind of a do-it-yourself model for those of you that have to get Mongo data to Snowflake or some data warehouse. We talked about the types of components that you'll likely need to consider to make that work. So the Upsolver approach is to manage much of this for you, right? So Upsolver does provide direct integration from MongoDB to Snowflake without having to manage some of the components that I referenced in the do-it-yourself approach, right? So if you don't want to have to worry about managing your own Kafka topic or event broker, and you don't want to have to worry about developing Snowpipe or Stovepipe streaming, code to handle data ingestion, Upsolver can go straight from MongoDB to Snowflake and handle that ingestion process for you. One real nice advantage of the Upsolver approach is that we allow you to control the write interval to Snowflake. I don't know of a single Snowflake customer who isn't at least in theory concerned of Snowflake cost. And many customers, after they start running production workloads on Snowflake, they eventually will come up against a project to try and reduce that cost. One of the things that can drive up Snowflake cost the most is very frequent merge commands coming from CDC sources. Right? So in Upsolver, you can map your interval, your write interval to Snowflake based on your business requirements. If you need near real-time data, we will write near real-time data to Snowflake. But if you don't, you might be able to save some cost by saying, let's only write MongoDB data to Snowflake once every 4 hours or once an hour, maybe even once a day. And that will dramatically bring down your Snowflake costs because the warehouse doesn't need to be running 24/7 to process all of this data ingestion. Right? We'll show you some examples of schema evolution here as we get into the demo, but when we talk about that kind of data modeling schema mapping conversation from the last few slides, Upsolver is going to handle a lot of that for you. So if the schema does evolve in the source Mongo system, your pipeline will most likely not need to be modified to incorporate the modified schema. But if you do need to modify the schema and do some more direct mapping of data from source to target, Upsolver does allow for both an ELT ingestion, where we load data into Snowflake as is, or an ETL ingestion. And sorry, I just realized the typo on my slide. This should say ETL. So we can kind of do either or based on your business requirements, right? If you just want to get raw data to Snowflake in a variant column and let Snowflake transform it after the fact, we'll do that ELT for you. If you want to handle some of that transformation up front and do it very cost effectively before loading that data into Snowflake, we can do that too. And I'll show you an example of both as we get into the demo. Lastly, whenever you kind of build your own data integration architectures, one of the last things to often get built is any type of observability and monitoring, right? And once these data pipelines go into production, it becomes critical to understand whether or not they're working, right? Whether or not the pipeline itself is working and keeping up and scaling as needed, but also whether or not the data that we're ingesting is of a high quality, right? And so Upsolver gives you effectively, Upsolver effectively gives you the ability to observe and monitor the overall health and status of your ingestion processes, as well as the quality of data that's being written to Snowflake. So those are some of the key key components and key value propositions that Upsolver gives you when ingesting data from MongoDB to Snowflake. And just to overlay some of what we just discussed on top of a more do-it-yourself architecture, if you look at your sources on the left-hand side of the screen and your targets on the right-hand side of the screen, again, many customers are very successful building it themselves using a variety of technologies that you see in this red box in the middle of the screen. But if you're looking to really simplify that process and leverage a single solution to get data from source to target without having to manage Kafka or Debezium or Spark or Snowpipe or build your own automation or build your own monitoring, that's really where a lot of Upsolver's value proposition comes in. So with all of that as the backdrop, let's show you how this all works. So I'm going to switch into a demo here, and we're looking at the Upsolver interface here, which is all web-driven. And I'm going to first just kind of bring you through the simplest integration that we offer, right? This is kind of that ELT integration I alluded to, where we just want to get raw data from MongoDB into Snowflake as easily as possible. So we'll step through this MongoDB to Snowflake wizard. The wizard has 3 components to it, and we'll start with connecting to MongoDB. I'm going to use a connection that I've already created here, but if you don't have an existing connection, it's very simple, just a connection string and some authentication to Mongo, and that will allow us to leverage that connection in our data ingestion. Step 2 of the wizard has us select which databases and collections we want to ingest. The default is to ingest everything, right? Including newly created databases and collections. You'll see these automatic options. This is one way that Upsolver can handle schema evolution at the source, is by simply leveraging the automatic options to say, even if a new database is created or a new collection is created after this job is set up, I want it dynamically added to the ingestion process, right? We see that very commonly used with customers who really just want to replicate all of their data to Snowflake and don't want to have to create or modify their pipelines when new collections are added. The next section of the wizard is to connect to Snowflake. Again, very simply, I'm going to use a connection that already exists, but I could build a new connection if needed. It's just a connection string, username, and password. And we're going to map our MongoDB collections into a Snowflake schema. I'll just use my schema here, J Hall. And I'm going to give every table a prefix of Mongo. This isn't required by default. The table name in Snowflake will be the same as the table name in Mongo. But I just want to keep things a little organized and more easier to find. So I'm going to give every table a prefix of Mongo. And the last screen in the wizard here is where we can configure the ingestion itself. Specifically, how often do I want data to be written to Snowflake? Again, going back to maybe cost control, this is where you can balance your business requirements to data freshness. Maybe we only need data once an hour, so we can scale back our write interval, maybe save some Snowflake costs, but can still get data replicated once per hour to Snowflake. In my case, I'll use the default of once per minute. We can also configure how we're going to handle deletes. We do support both hard and soft deletes. A hard delete would delete a Snowflake row when the MongoDB document is deleted. A soft delete would leave that data in Snowflake, but just mark it as deleted, right? Which is a common approach for data warehousing. And then down below here, you'll see an event timestamp that we can add to every row within Snowflake. What this is really useful for those scenarios where your data may not have a timestamp that you can perform incremental transformations on. Upsolver can actually add one for you, right? If you want to do aggregations based on time in Snowflake, this provides a guaranteed ordering of rows with a guaranteed timestamp column that can then allow you to perform transformations. So those are all things that you can configure in your ingestion job. When you click next here, what Upsolver will do for you is build the code needed to create this ingestion job. Some customers aren't overly concerned about the code, in which case you can just click run and go. But if you are concerned about the code or want to reuse this in maybe external processes, maybe run this code through a Python SDK, which we provide, or a CLI, maybe you want to check the code into version control. Maybe you want to automate the code through your CI/CD processes. You know, the wizard generates code that you can then build on top of or use externally to Upsolver. But in my case, I'm just going to go and create the job. We get an indication here that the job has been created, and there's a link here to start monitoring the job process. Okay. So this job is now created, and there's two components to a CDC pipeline in Upsolver. There's an input job and an output job. So what we're currently looking at is the status of the input job. This is the reading of MongoDB data into Upsolver. And this reading will start with a snapshot process. So I've got two collections here included, inspections and orders. Both of these readings pending. Upsolver is currently kind of getting things ready to start snapshotting. Once everything's ready, you'll see the status of the first collection change to snapshotting. That tells you the initial snapshot is starting to take place. Once the snapshot is complete, the status will change to streaming. And that tells you that the snapshot is now done and we're now streaming change events into Upsolver that can be processed. Right? This process will take anywhere from a few seconds to a few minutes to maybe even hours, depending on how many collections and how big each of those collections are that need to be processed. While I wait for that to happen, I will take one step back. I know we're focusing on MongoDB on today's call, but I do want to make sure that everyone's aware that we do support ingestion from a variety of data sources, right? On the database side, we support MySQL, PostgreSQL, Microsoft SQL Server, and MongoDB. We also support direct ingestion from streaming sources, specifically Kafka and Kinesis. And we also support ingestion from object storage on S3. So a lot of those kind of big data, complex, high-scale data sources, we can do very similar data ingestion through similar wizards like you saw with the MongoDB example. Okay. One question that's actually already come through, I'll answer that here because it's relevant. I mentioned ingesting data from Mongo into Upsolver. And somebody had actually asked, what does into Upsolver mean? That's a great question. So architecturally, there are two ways that you can run Upsolver processing. One way is that you can run processing in Upsolver's cloud, right? Think of that as a SaaS deployment where the data processing and pipeline management happens externally, or I should say internally to Upsolver, externally to your environment. So if you want kind of that true SaaS model where you don't want to have to provision anything, you just want everything to run in our cloud, you can use Upsolver's cloud for data processing, and then you simply just have to build your connections, and we will process all the data for you. That's a very common approach, especially for testing, evaluation, proof of concepts. But we also do have production customers that will run Upsolver in that way. The other way that you can run Upsolver is that you can run Upsolver in your cloud account, in your AWS VPC. You'll see a Start Integration button should you want to do so on the Cloud Integration page. That Start Integration will ask you a few questions about your AWS deployment, and then it will provide you with a CloudFormation template that you can use to deploy Upsolver resources into your cloud account. The nice thing about that is then you have full control and full governance over all of Upsolver's data processing. All right, so if you have strong security requirements, if you need to protect PII, if you need to make sure that firewalls are configured so people don't have access into your data, you can deploy Upsolver into your VPC, and then all of the controls and practices that AWS offers to protect your data can apply to your Upsolver data processing. Right. So very good question. Again, two methods for managing Upsolver and working with data pipelines. One is to run them in our cloud as a SaaS solution. The other would be to deploy Upsolver into your VPC, and then you can run Upsolver in your own AWS account. So with that said, we can jump back into our input job here, and you can see the first snapshot is now complete of my orders table. Looks like it's getting started on the snapshot for my inspections table. Within a minute or so, I expect that to be complete, and we'll see that data start streaming into the Upsolver platform. Right. Now, the other side of a CDC job, I mentioned the input side here is an output side. All right, there's an output job. And so if I look at my jobs list, you'll see those two jobs here. The output is what we kind of refer to as a parent job. And underneath the parent job, you'll have an output job for each Snowflake table that you're writing into, or each MongoDB collection. It's a good way to think of it. So far, I've started writing my orders data to Snowflake. Very soon after that inspection snapshot is completed, we'll see the inspections snapshot start writing into Snowflake as well. And so you can monitor the status of data being written into Snowflake as well, right? By clicking on the output job. Here we can see this output job to the orders collection. It's written 665 rows to Snowflake, and we'll get some helpful data processing and error handling graphs that we can use to measure the throughput of our pipelines and also debug and troubleshoot anything that maybe isn't working as expected. All right. Again, in the introduction, I managed observability into pipeline processing. This is a lot of what I was referring to, right? That fact that when you build your pipelines, you can then monitor and observe the health of those pipelines through our job monitoring interfaces. To kind of see the end result of this pipeline, I'll actually switch over to my Snowflake console here, and I'll refresh my catalog here and see that sure enough, now inside of my JHall schema, I've got this Mongo orders table. You can see it was created a few minutes ago. It has 665 rows in it. You saw that from the Upsolver side, but here you can confirm that from the Snowflake side. And if we want to query that data, we'll go ahead and take a look at it within Snowflake. Here's the top 10 rows from that orders table in Snowflake, and we can see the data as it was from Mongo. Now, if you remember, I mentioned I was going to start by showing you the simplest way to ingest data from MongoDB to Snowflake. All right. More of that ELT model. Let's get raw data from Mongo into Snowflake as easy as possible in its raw form. And in order to do that, you can see how the schema has been mapped, right? For the root fields in the data structure, like net total, order date, order ID, we've just added Snowflake columns and mapped them to the most appropriate data type, right? But for the nested and array structures within the source data, we've created a variant column. If I look at the definition of this Mongo table that was dynamically created, you'll see the customer and data column here are a variant type. And we've taken that nested JSON structure and added it to a variant column within Snowflake. We can now parse and break this out in further transformations. Similarly, with the data column, that's our items array. And you can see the items array has also been written into that variant column. So that's how kind of the automated schema mapping is going to work within this ingestion pipeline. Now, if we just want to kind of finish out the use case, remember, we started this quote unquote project because we wanted to run analytical queries against Mongo data. We described why that's a little bit difficult in Mongo. This is a very small use case, but just again, to maybe finish the example, we can now take the Mongo data that we've replicated into Snowflake, convert the order date into a minute truncation, run some aggregate functions against it, and now have an analytical query that can maybe be used to feed some sort of business intelligence dashboard or report. Right, here's the quantity of orders per minute from our source data. So that's one example, right, of a very simple pipeline, reading data from MongoDB, writing it into Snowflake. Now, I mentioned that was the simplest way. What if we want to do some more, I don't want to call it more advanced, because honestly, it's not overly difficult. But I will say, what if we want to do a bit more manual data mapping? And so I wanted to show you kind of the two most common use cases in converting data from some sort of semi-structured JSON form into a Snowflake table. The first would be unnesting nested JSON. All right. And here's an example of a job that can do that in Upsolver. The first few lines of this job are more configuration based. But if you look at the select statement here, transformations in Upsolver are defined using SQL. So unnesting of JSON, right, taking nested JSON fields and mapping those to separate columns is really just an exercise in mapping those columns from the source to the target, right? So customer.address.city, that's the nested structure from the source MongoDB document. We're going to extract that field and write it into a separate column called city, right? Another thing that you might need to do, not necessarily related to nesting, is data type conversion, right? And so maybe, for example, you've got postal codes as both strings and numbers. You could do something like toString city, or sorry, customer.address.postcode as customer postcode, right? And now you're kind of forcing all of this field into a string data type that's now consistently written into Snowflake. You can also see some common transformation practices like maybe hashing of PII, right? Email addresses, if I go back to my original table, let me, again, query the original data from Snowflake. If you look here into this nested customer field, you'll see eventually when we get to the email address that we've got actual email addresses written into Snowflake. We might not want that. We might want some hash of the email address so that that potentially sensitive data is protected. So in our transformation logic, we can apply an MD5 hash to the email address and write that into Snowflake, right? And so all of this can be done now with a fairly simple SQL statement. And then that SQL statement can be used to transform MongoDB data as it's written to Snowflake. And if I look at the results of this job, it's this unnest table that we have created. You'll see that we've now have a Snowflake table created with those modifications that we've specified, right? Notice customer city is now a separate column, right? It's no longer inside of the variant column, it's a separate column. Notice that customer email, not only is it a separate column, but it's been hashed using that MD5 algorithm, right? And so on. So if your use case for taking data from MongoDB to Snowflake involves unnesting of nested data structures, it's really just as simple as a select statement that maps your source columns to your target columns. Now, maybe a little bit even more interesting is how are we handling those arrays? All right, there's a few different ways to do it, but let's say we want to flatten an array. We want to take each array element and create a separate row for each element within the array. Well, that's also fairly straightforward and involves the use of this unnest command in our transformation logic. Right? The rest of this job is more or less the exact same as what we saw above, but here we just have to call unnest We again have to map our source columns to our target columns. But when we use unnest, if we switch over to Snowflake and look at the flattened table, you'll see for each item within the array, we now have a separate row. And here's an example. If you look at row 5 and 6 here, we have 2 order IDs. Without unnesting this data or flattening this data, we'd have 1 order ID with a data column that includes a variant block of JSON with an array element inside of it, and that array has 2 items. Flattening the data creates 2 order IDs, 1 per each item in the item array with the corresponding data associated with it. And one of the reasons why you may want or need to flatten an array is that so you can then perform analytics and aggregations on each array element. For example, a use case like this, we want to query from Snowflake, not by order ID, but by item ID within each order, right? What are the highest selling items within each order, not the highest selling orders, right? And once the data is flattened, that becomes a much simpler analysis for Snowflake to do. We can run a simple query now, grouping by the flattened column. And now for each item, we can see how many orders and what's the total sold for that particular item ID. So I wanted to show both of those examples, right, from a demo perspective. Kind of the ELT option of very simply taking raw data from Mongo, writing it to Snowflake, the use of variant columns to make sure that we can automatically map schemas. And by the way, if the schema evolves on the source, this will automatically get applied to the target. But then also showing some fairly basic use cases around the unnesting of nested data structures and the flattening of array elements as data is being written into Snowflake. The last thing I wanted to highlight when it comes to observability is that we've shown you observability into the pipeline itself. We also provide observability into the data that's being written into Snowflake. For example, if we go into any of the Snowflake tables that we've shown here that we're writing data into, let me go into my JHall schema here. There it is. We can go into that Snowflake table that we're writing data into and see all of these statistics that were automatically created and presented to you during the ingestion process. Right? Each of the fields that we're writing into Snowflake, we're showing you what's the data type of that field. We're showing you the density of that field, right? How often does that field show up in each MongoDB document, right? 100% density means that this customer address city is in 100% of our MongoDB documents. But this items ID discount rate only appears in 24% of our MongoDB documents, right? So we can look for the presence of null values or maybe an evolving schema in that new fields have started showing up, or it's just not every MongoDB document contains the same set of fields. We can also see things over on the right, like these timestamps that are shown, right? When did we first see that field within a MongoDB document? And when have we last seen that field within a MongoDB document? This would give you some visibility into the fact that maybe we've been ingesting this data for 6 months and all of a sudden we're now storing a new field within Mongo that has never been stored before. You'd see the exact timestamp of when that field first appeared in the MongoDB source. Similarly, if we stopped recording field names in Mongo, you'd see the last time that field showed up. Maybe a Snowflake user is starting to complain about why some data is missing in their dashboards. Right? This would give you some visibility to the fact that the data has stopped showing up in Mongo, I don't know, 2.5 days ago, right? Because the timestamp is lagging, what the current timestamp is. So we really do give you a lot of nice observability, not just into the pipeline operation itself, but also into the quality of data that's being ingested from source to target. So that's what I wanted to show in the demo. To kind of wrap up, and then I'll go through any questions that everyone else might have. I'll just leave you with kind of some next steps. First off, and I'll go ahead and send these links through in the chat in just 1 second. We do support fully functional cloud-hosted trials in our sandbox environment. So anyone who would like to take a look at Upsolver, maybe try working with your own data sets. We also do provide some sample data sets for those that might want to just work with some of our samples. We do support a trial off of the Upsolver website, fully functional. Really, all you have to do is sign up and get access to the platform. If you want more of a guided experience, we do run once a month. We run hosted workshops. The next one is coming up in 2 weeks. I believe it's September 27th. I probably should have put the date here in the slides. But I believe it's 2 weeks from now, September 27th, we will be doing our next hands-on workshop. That's a really good opportunity for those that might want to get more familiar with Upsolver and use the product, but kind of be guided through a few different hands-on scenarios. The workshops do a good job at that. And then lastly, anybody who does have comments or feedback, please do feel free to reach out to me directly. You can see my email and my contact information there on the slide. I would welcome the opportunity to answer any questions that you have or work more with any of you that might want to take a deeper look at Upsolver. Okay, I'm going to go ahead and just send these links through in the chat so everyone has them handy. And then I'll go ahead and answer any questions that anyone does have. And for those of you that do have questions, please send those through in the Q&A function of Zoom, and that will let me know that you have a question. I already answered the question about where does Upsolver run. Just to confirm, it can either run in our cloud-hosted model or, our cloud-hosted offering as a SaaS solution, or it could run in an AWS VPC that you deploy Upsolver to through a CloudFormation template. There's a question about licensing. Our pricing is available on the Upsolver website. If you go to www.upsolver.com, there's a pricing page that'll walk you through it. Just to kind of simplify it, there's two components to an Upsolver license or pricing. One is there's a software fee, which is a flat cost based on the features and level of support that you need within the platform. So you can go to that pricing page and just kind of match yourself to either our startup, standard, or enterprise edition. And it'll show you what the breakdown of features and support is in each of those. But that will be a fixed cost. So once you sign on with Upsolver, you know exactly what that is month over month. There's then a variable cost to the Upsolver licensing model, and that's based on the volume of data that we ingest. And it's priced out per terabyte. So depending on how much data you think you might be working with, you can kind of do the math there. It's pretty linear math. But it's priced out per terabyte. You can see what the per terabyte cost is on that same pricing page on the Upsolver website. So go ahead and check that out if you want to learn more about our license model. And if you do have further questions, feel free to reach out to me and I can walk you through an exercise on what it might look like for your use case. There was a question here about, let me just read through it. Oh, okay. There's a question here about combining MongoDB data with other sources. Yeah, great use case. So there's two ways that I see customers doing that. Some of your data comes from MongoDB. Maybe some of your data comes from PostgreSQL, or some of your data comes from a file sitting on S3. There's two ways you can do that. You can use Upsolver in more of the ELT model that we showed, right? Where let's get all of your data from Mongo and from Postgres and from S3 into Snowflake, and then we'll create all of our transformations and joins in Snowflake itself. Or you can use the ETL model that I showed you, where we get all of the data into Upsolver, and then we can process joins and refinement and enrichment of data within Upsolver transformations. Transformations, again, you saw a simple example of a transformation using SQL. Combining of data sources is very similar. You would write a transformation that joins two different sources that you've read into Upsolver into a single result, and then writes that result into Snowflake. So easy answer is yes, we can join or combine multiple data sources. The question is, would you rather do that in Snowflake, or would you rather do that prior to data being written into Snowflake and do that in Upsolver? And we can do both based on what's the best fit for your use case. Last question that I see, and then we should be able to wrap up unless anyone else does have any final questions. Feel free to send those in. But the last question is about what additional targets do we support? Good question. We talked very heavily about Snowflake today, but that I don't want to imply that that's our only output or target that we support in Upsolver. The current list is that we can write data directly to Snowflake or to Redshift. Those would be the two primary data warehouses that we support. We also do support writing data into a managed data lake, which is a data lake that Upsolver will manage for you. It's a really nice option for customers that want, transform data into a data lake output and then query that data using something like Athena or any sort of data lake query engine. And Upsolver will manage that data lake for you. We'll make sure that's an efficient process, handling data retention, schema evolution, compaction, all the typical difficult things in managing data lakes. Upsolver will automate a lot of that for you. So we support Snowflake, Redshift, we support managed data lake outputs, and then we also support outputs to just raw S3 files. We support outputs to Elasticsearch, and finally, we support outputs to PostgreSQL. And that list will likely continue growing as our roadmap allows us to add capabilities based on customer access, or I should say customer requests. Okay. Last question that just came through, will you have access to the slides? Absolutely. I'll make the slides available. We also recorded today's call, so we'll post the recording out to our website for those that might want to catch up on anything that you might want to miss or refer back to. The recording will also be very easy for you to share with any colleagues or coworkers that maybe couldn't attend today's call. So definitely make sure that we post that. And if anybody does have any further questions or is having trouble finding the recording or finding the slides, again, you've got my contact information there on the slides. Hopefully you've jotted that down or taken a screenshot, and feel free to reach out directly if you do ever have any questions, comments, feedback, or anything that I can possibly help you with. So I appreciate everyone's time today. I'm showing just a little bit past the top of the hour. So thanks for sticking with us for another few minutes. And I look forward to working with you in the future. Thanks, everyone.